Good afternoon, everyone. My name is Kapil Karkra. I'm from Intel Corporation. In last year's Flash Memory Summit, we talked about how Intel Optane Media provides data centers with the ability to increase endurance while reducing costs and boosting performance. And endurance directly impacts operational costs. For example, improved endurance can translate directly to lower TCO without sacrificing performance. And we also said that for many data centers, the best balance of performance and cost can be attained by deploying Optane with NAND. The work that we are presenting today provides a mathematically precise theory about conditions under which a workload will benefit from deploying both Optane and NAND. As far as the organization of this presentation, we have three parts. In part one, I will get into the theory. Then in part two, Michal Wysochansky will apply this theory to three popular databases, RogueDB, MongoDB, and MySQL as proof points. Last, Mariusz Barczak will conclude by getting into our generic tiering algorithm that, without knowing what database or workload is running on top, can automatically classify and tier across Optane and QLC. On this slide, I want to clarify a few terms to give you some intuition about conditions under which a workload can benefit from Optane. The table on top right shows how the endurance and performance drop as we go from TLC media to QLC media. The endurance and performance of QLC drop about 3x. Optane with 5% capacity can provide the same endurance as TLC. So 375 gigabyte Optane versus an 8 terabyte TLC, same endurance. The idea with the placement across Optane and QLC is to balance performance and cost. When we say on the table left-hand side O plus X greater than Y in the first term over there, we really mean O plus Q as a tiered hierarchy is better than TLC. Next term, occupancy, is the amount of storage space that the workload occupies. If you write 4 gigabyte file and delete it and write it again, the actual occupancy is just 4 gigabytes, even though you wrote 8 gigabytes. In a tiering scheme, alpha or WRF is the write reduction factor. It is the percentage of bytes written by workload that go to Optane. WIF or beta is the write invalidation factor. It is the workload bytes written divided by the occupancy. It is an indicator of write locality or data lifetime. Let's walk through now the bottom right example. It's a toy example where a workload writes 100 gigabytes of space 60 times a day. So endurance demand for this workload or beta is 60. Optane endurance is 60 drive writes per day. So demand matches the capability. And so we need 100 gigabytes to sustain this workload. At $2 a gigabyte, we would spend 200 on Optane. Now, standard TLC flash, for example, Intel P4510, where endurance is 1 drive write per day, we would have to buy 60 times 100, 6 terabyte storage. At 10 cents a gigabyte, that would cost us $600. So $200 Optane versus $600 TLC flash. It is a no-brainer that if certain data classes in the workload have endurance demand higher than a beta cutoff, and the cutoff in this case is 20, placing it on Optane will be cheaper and faster. Now I want to drill down on our two key metrics, alpha and beta, a little bit more. So let's drill down on this slide on alpha and understand how we make endurance of O plus Q better than the endurance of T. Here on the top left first, the workload is hitting TLC, and this workload has the available budget of 44.25 petabytes that it can write over the life of the TLC SSD. To QLC, we can only write 12.3 petabyte out of this 44.25. The rest must go to Optane. And if this workload is not pure sequential and rather random, you might only get 13.88 petabytes out of TLC. So let's see what we need to do to achieve this balance. First, we need to pass the workload through a data classifier. This is what I'm showing on the diagram at the bottom. And this data classifier will classify hot and cold data. Our placement engine in this case is OpenCAS, and it knows how to consume these classes and place data across Optane and QLC. So intuitively, we will continue to turn this dial and increase alpha, which is the percentage of writes that go to Optane, from 0 to a minimum acceptable level called alpha min. where the percent life consumed by workload on QLC is equal to the percent life consumed on TLC. As we further turn the dial and increase alpha, we will reach an optimal point, alpha optimal, where we wear level across Optane and QLC equally. In this case, endurance of O plus Q system will be additive. And if we continue to increase alpha, we'll reach the farthest point, alpha max, where O plus Q is still competitive with T. Note that now Optane will be the limiter of endurance between alpha optimal and alpha max. So the O plus Q system stays competitive with T for all values of alpha between alpha min and alpha max. And in practice, we have found for database workloads, this alpha min lands somewhere between 50 and 65. So obviously, first workload condition is this alpha min, where workload must have a classifiable percentage around 50 to 65%. Let's now drill down in beta. Requirement number one, we already talked about alpha min requirement. We must have a classifiable percentage 65%. Now, let's talk about the second requirement, which we call cost constraint. For O plus Q to be price competitive with T, the O size must be 5% of the TLC capacity. To meet both requirements simultaneously, the writes going to Optane must be shorter lifetime. That means they must have beta higher than some cutoff. To intuitively see what this means, let's take an analogy. Compare Walmart Supercenter store with a small 7-Eleven-like store. And let's say the constraint is to generate same amount of sales from both stores. In this case, the items one would keep in a small 7-Eleven store would naturally be items that sell like hotcake. And their shelf life is so small that they fly out of store and people line up to buy those items. So we sell those items, make room for next set of items, and we keep doing this. It is the same idea here. We should place on Optane media the files and objects that are deleted within seconds and make room to stage new objects and files. Their lifetime is so small that overall volume of writes can be 50 to 65% with the small store capacity no more than 3 to 5% of the Walmart's superstore. So to summarize, two workload conditions under which Optane plus QLC will be better than TLC. One, workload must have a classifiable portion alpha greater than alpha min, and we have observed this to land somewhere between 50 and 65%. And two, the aggregate beta of these writes redirected to Optane must be greater than some beta cutoff. Their size should not exceed 3 to 5% capacity. With that, I'm going to turn it over to Michal Wysochansky to cover part 2 of this presentation.
Thank you, Kapil. Hello, everyone. The math and theory Kapil just described is mainly for optimizing endurance. But in addition to that, it also provides some performance improvement. This is because of several reasons. First, write performance for random writes would be optimized by Intel Optane SSD. A lot of random writes will be capped by Optane SSD, thus providing better endurance. There is also improvement for read after write behavior. If some data is read shortly after it's been written, the Optane SSD would provide better performance. The same applies for read QoS and latency. Because of significant write reduction, QoS and latency would be better. Last but not least, we have two devices available instead of one. So the bandwidth available for application would also be better. This was just a theory. But what about practice? We wanted to prove our theory by running a set of experiments, by verifying it using few popular database engines. The first one we tried was the RogueDB. RogueDB is a popular key-value database, or key-value store, if you like, which uses LSM as a data structure. So we wanted to find out if there is a set of data created by RogueDB that meets our requirements for alpha and beta. And we find out that write-ahead log and upper levels are pretty small in terms of capacity, but most of writes are targeted to those levels. As you can see in the table on the right, almost 80% of writes are targeted to pretty small LBA range, pretty small capacity. So we wanted to build a classifier to pin this data to Optane while bypassing lower LSM levels to QLC drive. To do that, we use the mechanism from Linux kernel called write lifetime hint. This mechanism allows application to pass a hint to a storage stack about the meaning of the data. And the higher levels are marked with different hints and lower levels with another one. We used open cache acceleration software to interpret that hint and put data accordingly to it, either on Optane or on backend storage, in this time QS. Thanks to that, we are able to achieve better endurance, better performance, both in terms of bandwidth and latency, both average and tail. The next database we tried was the MongoDB. The MongoDB is a popular NoSQL database. We used YCSB benchmark with workload A to measure the performance and endurance. We identified that in MongoDB, a lot of writes are targeted to journal, which is pretty small in terms of occupancy. More than 90% of write is targeted just to 5 gigabytes of capacity, while the rest, few percent of writes are targeted to more than 700 gigabytes. So we placed the journal on the Optane drive and bypassed the rest of the database files to the QLC drive. In this case, as a placement engine, we used classifiers based on directory policy, because in MongoDB, the journal is placed in different directories. So we were able to identify journal just by interpreting the path of the files. And the results we get are in the table on the right. As you can see, we are able to get much better endurance, but also performance. And again, both in terms of throughput or bandwidth and in terms of average and tail latency. And the third database we tried was the MySQL. This is very popular SQL database. We used Sysbench with TPCC benchmark. Similarly to MongoDB and RogueDB, we tried to identify which files or which data we want to put on Optane and which data should go to QLC. We identified Redulog, temporary table space, and also MySQL system database, which contains a double write buffer. After analyzing the workload, we found that just pinning those 3 files or 3 portions of data, we are able to capture more than 50% of writes. And again, this data is relatively small on the disk, so it's perfect candidate to be put on Optane. But in this case, 56% of writes is not enough to beat TLC endurance. So the endurance of the whole solution is slightly below the endurance of pure TLC drive, but performance is still better, both in terms of transactions per second and in terms of latency, both average and tail. All right. So these were the three cases, three databases we tried to analyze and verify our theory. For those three databases, we created the classifiers manually. We analyzed the workload, we analyzed the database structure, and we created the corresponding classifier. But we also developed some tools that allows you to automatically figure out what should be the best classification schema and what to put on Optane and what should be put on backend storage. And Mariusz Balczak will describe this to you.
Okay, now let's see how we can make this theory working in the action. First, we collect IO trace, which contains block device telemetry and file system telemetry as well. Then we can parse this IO trace. And because IO trace is rich, we can build various IO classes. So we can classify IOs, for example, by directory or file system extension. Then for each IO class, we can calculate write invalidation factor, and we can sort IO classes by width, starting from the highest to the lowest. And we can select IO classes with the highest width, which fits to the available Optane capacity. The last step is checking our write reduction factor. And if it's higher than 16%, it means that we are ready to go and we can put our workload on Optane plus QLC deployment. We tested this algorithm for various databases, for various applications, and we got the same results like Michał got. So for example, for MongoDB database, we indicated journal directory as this one, which is supposed to be placed on Optane. Okay, now let's see how we introduced this algorithm to our storage stack. In this case, we run OpenCAS storage cache, and we collected IO traces using standalone Linux IO tracer, and we stored IO traces into our telemetry framework database. Then we parsed the IO traces, we classified the data, and we checked write invalidation factor for each IO class. At the end, we got the list of IO classes which are supposed to be placed on Optane tier. Then we can reconfigure our cache, and starting from this point, our placement engine is able to distribute the workload across two tiers. The first one is Optane and second one is QLC. Below, there are links of our tools which we built in order to make this algorithm working in our storage stack. Now, let me conclude this presentation. We shared the theory how to distribute the workload between Optane device and NAND devices. It allows you to get the higher endurance for entire storage solution, as well higher performance numbers of your workloads and applications. We prove it is working for popular databases. As well, we developed open source tools which introduces this theory and can be integrated into any storage stack. On the basis of these tools, you can configure your storage software and you can get higher endurance and higher performance. So feel free to check out our open source tools to test our O plus Q theory and let us know how it is working on your side, on your workloads. Thank you.